Hi class, today's lesson is on percent composition and empirical formula. So, good evening everyone. As I mentioned in the post, we were going to be covering 7.1 and 7.2 depending on our time. We may go through 7.3, but we're not really in a rush for that. Okay, if we get there, we get there. If we don't, we don't. Okay, so let's look at 7.1. 7.1 percentage composition. If you want, you can have a calculator, let's say, with you, so you can kind of follow along with any of the calculations that we do. But let's get to it. So, in chemistry, the law of definite proportions, sometimes referred to as Proust's law or the law of definite proportion, states that a chemical compound always contains exactly the same proportion of elements by mass. So, what does that mean? Okay, so that's the textbook definition of the law of definite proportion or Proust's law. I don't really care about it with regards to Proust's law. I just know it as the law of definite proportion. So, what that means is that take, for example, the sample problem that I have here at the bottom, okay? That the composition of this formula is going to be exactly the same for every water molecule based on the composition or percent composition of hydrogens and oxygens in the entire formula, okay? So what you're doing is or what it kind of entails is that we are really finding what's referred to as the percent composition of the atoms in a particular formula and the percent that which they exist. So so take for example this sample problem that I have here, H2O. If we find the mass of all water, and we talked about this last class when we were looking at the molar mass, right? Molar mass of water is 18.02 grams per mole. Okay, so we've got grams per mole, the unit. So we're finding the molar mass. You find it using the atomic masses of two hydrogens. You add it to the atomic mass of oxygen, and that's where we get the 18.02 grams per mole. Now, this is the overall mass of water. Now, to calculate the percent composition, we are looking at all the atoms in that entire compound's formula. So we're looking at the hydrogens, and we're looking at the oxygens. So what we're going to do is we're going to take the masses of the hydrogens. Okay, so there are two hydrogens. Each hydrogen is 1.01. Right? So each hydrogen, so hydrogen is equal to 1.01 grams per mole. But there's two of them. So we're going to multiply that by 2. Okay? And we have oxygen, which has a molar mass of 16.00 grams per mole. So when we add these two up, that's where we get our 18. But if we want to find the percent composition, we're going to take the 2 times 1.01, so that will work out to, so if we've got 2 hydrogens, that would work out to 2.02 grams per mole when we multiply it by 2, because there are 2 hydrogens. And what we would do is we would take this 2.02 and we divide it by 18.02. So it's kind of like calculating the percent that we get on a test. So we take all the, so if a test is out of 50, and we score 40 out of the 50, right? How do we calculate the percent? So we take the 40, we divide it by the overall number of marks. So we take what we get, divided by the overall number of marks, and multiply it by 100. So in this case, the overall is the overall molar mass of our compound. The what did we get part is, well, what are we looking at? Are we looking at the hydrogen in this example, or are we looking at the oxygen? In this case, we're going to be looking at both, but individually. So if we take the 2.02, we divide it by the 18.02, and then we multiply it by 100, we will get our percent of hydrogen that is found in water. We take the 16.00, we divide it by the 18.02, multiply by 100 to find the percent, and we would get the percent composition of oxygen in water. Notice how oxygen makes up the majority of the mass of water. So I don't know if the answer is on this next slide. Let's see here. So actually, it's in this slide. So here is the calculation, okay, or the answer to that calculation. So Proust's law, the law of definite proportion, which states that for every compound that has a ratio of 2 hydrogens for every 1 oxygen, as in the case of water, 88.79% of this formula is made up of oxygen atoms. The remaining 11.21% is made up of hydrogen. Okay, and if you looked at the percent composition of another compound that also contains hydrogen and oxygen. So let's look at another example. So I'm going to write it up here. So let's look at hydrogen peroxide. Okay, if we're looking at hydrogen peroxide, and I'm not going to put the subscripts just because I took away that folder or that part of the menu, and I don't want to go look for it. But anyhow, the overall mass of this will be completely different. Okay, so remember that the mass for water worked out to 18.02 grams per mole, but for hydrogen peroxide, however, right, we still have the 2 hydrogens, right, and that will be equivalent to 2.02 grams per mole. But we would now add it to 2 oxygens, which each oxygen is 16, so we'd have a total of 32.00 grams per mole. So the overall mass of hydrogen peroxide will be 34.02 grams per mole. So if we took the 2.02 and we divide it by this, we are going to get a different percent composition for this formula. So the definite proportion means that if we have, for every 2 hydrogens and 1 oxygen that we have, we will always have this as a percent composition. If we had 2 hydrogens for every 2 oxygens, as in this case, we will have a completely different percent composition. So going back to the definition, they will always have the same proportions of elements based on their masses, right? So even though in this case, both examples contain hydrogens and oxygens, the ratio of hydrogens to oxygens vary. And because they vary, it will lead to different percent compositions for each atom in that formula. Okay, let's look at another example here. Carbon dioxide and carbon monoxide both have the same number of elements, but the proportion of carbons to oxygens are going to be completely different because in this first case, right, CO2, we have an additional oxygen. So that additional oxygen will translate to a larger mass, larger molar mass, in which case it will change the actual overall percent composition of carbons to oxygens. Okay, so the percent composition of a compound refers to the relative mass of each element. So a compound's percentage composition can be a valuable tool to identifying the formula of an unknown compound. What that means is, if we knew the percent compositions, we could work backwards and figure out, ballpark-wise, what could be the formula of this unknown compound. Okay, so in forensic science, using mass spectrometry, they can find the percent compositions of these elements and be like, hey, this compound contains, I don't know, let's say 62% carbon. It contains 12.7% hydrogen, and it contains whatever remaining. I don't want to say a number because I'm not really thinking of the overall 100%, like for this just off the top of my head type of example. But using those three percentages, we could figure out ballpark wise what that possible compound, unknown compound, could be. So at the scene of a crime, they analyzed some unknown substance and they realized, hey, it's got traces of carbon, hydrogen, oxygen in it. Okay, so what are the percentages that they exist? And then from there, they can kind of eliminate a bunch of different types of compounds and eventually slowly kind of identify the overall what is that unknown substance. So it's not like it's a machine that you'd be like, I just throw it in and eventually it tells me what it is, right? It'll give me data, and based on that data is what I would use to figure out what my unknown substance happens to be. Okay, so we're going to get to the sample problems. Okay, so we've got here two sample problems. And I've got them detailed answers, but we're going to go through them. My advice to you, just kind of follow along. I'm going to go through the answer key and the steps of how to go about answering it. So hopefully later tonight, or even probably better yet, maybe tomorrow or later this week, see if you can go back to these sample problems and answer them, or go straight to the homework and see, can I answer the homework questions with what I've learned or what my understanding happens to be. So let's look at let's look at each sample problem first. Okay, so here we have the first sample problem. A compound with a mass of 48.72 grams is found to contain 32.69 grams of zinc and 16.03 grams of sulfur. What is the percent composition of the compound? So when I ask for the percent composition of the compound, I am actually asking you to find the percent composition of every atom in the formula. Okay, so it's not just, sometimes I might say, what is the element, what is that one, let's say, like that, I might say specific, okay, find the mass percent of zinc, right? Or I might say, find the mass percent of just sulfur. But if I ask what is the percent composition of the compound, I am asking you for you to find the percent composition of every single element in a formula. So here's another example. Let me add to this. Let's say I asked you to find the percent composition of calcium carbonate. So in this case, I would expect you to find the percent composition of calcium, of carbon, and of the three oxygens. Okay, so let me get rid of that. So how do we go about answering this? Well, zinc translates to, there's 32.69 grams. The overall compound contains 48.72 grams. Multiply this by 100, and we get a number of 67 point and all that, but we round it to we round it to 4 significant digits, since there are 4 significant digits in our question. Now, you can answer part B, or the second part to this, right? Sulfur, in one of two ways. One of the most common ways that students will try to answer this, and this to save them time, and I don't recommend it, but it's your choice. You will not be penalized on an evaluation if you did it this way. Because there are 2 atoms in this overall compound, if I find one, the overall percentage of the 2 would be 100%. So instead of doing the math here, as I did for sulfur, why don't I just take 100 and subtract it by 67, or subtract 67.10 from 100 to give me the percent composition of sulfur. That would be correct. That is a correct way to answer the sulfur percent composition for this example. But the reason why I'm not a fan, I don't recommend it is, and the reason for this is typically, not typically, in the event you make a mistake here, if you mess this up, this will also be wrong using that method. Okay, so by doing the actual calculation, right, when you look at the answer that you get, the best way to do is now see, okay, did I do both of them correctly? Add the two up, they should add up to 100%. Understand that they could be off, right? If you're adding, whether you're adding the decimals, depending on how you round, sometimes the answers might vary by 0.1 or 0.01, or you might get a point like 99. What do you call it? You might get something like 99.9%. So you might not be exactly 100%, but that's fine as long as you get that close, like 99.9% for your overall. Then that should be fine. Okay. So next, any questions regarding this sample problem before we move on to the next one? Okay. Okay, so let's move on to the next one. I'll take questions at the end of this 7.1. So after this sample problem. Okay, next sample problem. Let's not give the answer key. Let's go straight to the actual question. So we've got cinnamaldehyde, and the formula is C9H8O. Don't memorize these formulas, okay? The only formulas I expect you to kind of know offhand are ones that are related to what we covered in chapter 4. So cinnamaldehyde, the formula is C9H8O. It's responsible for the characteristic odor of cinnamon. Determine the percent composition of cinnamaldehyde by calculating the mass percents of carbon, hydrogen, and oxygen. Step number 1. Find the molar mass of this entire compound. Then find the molar mass of just the carbons in this formula. And be aware that it's C9. So 12.01 grams per mole is the molar mass of one carbon. Multiply that by 9 to get how many the molar mass of all the carbons in this example. Okay, do the same thing with hydrogen. Do the same thing with oxygen. Okay, and then what you could do, as I did here. So here's the molar masses. So here is the molar mass of 9 carbons divided by the molar mass of the entire compound. Okay, so we divide those two, multiply it by 100, and we get 81.78. Here's why it's important to kind of be on top of my lectures. Answers that do, so if remember when we round questions, we round based on either significant digits rule or addition, subtraction, decimal places. Typically, it's significant digits. There are no numbers to reference. So when there are no numbers to reference, we always round to 2 decimal places. So remember that. Put a note, let's say by your laptop, somewhere where you're studying, that anytime there are no numbers in a question, so there's no number for you to reference for significant digits rules, always round your answers to 2 decimal places. Okay, anyhow, going back, so here's our answer. So 81.78% of the mass of this entire compound is made up of carbon. Okay, a tiny portion of the percent composition is made up of hydrogen. So we take the molar mass of 8 hydrogens, we divide it by the molar mass of the entire compound, multiply it by 100 to get 6.11%. Now, to find oxygen, and this, if you're confident with your math, if you're confident with your numbers, you could just add these two up, subtract them from 100 to get the percent composition of the remaining atom. I'm fine with that. Okay, as long as you show me that step, right? You do that 100 minus those numbers. That's the work. That's you showing me. And I was talking with someone, emailing someone earlier today, and I can't stress how much one of the things that I love about math is that there are many different ways that you can go about answering a problem. I'm always going to share with you my methods of answering problems. If you've taken this course before, or maybe you've kind of, you have a different way of thinking that, allows you, maybe you see patterns that I don't quite see, that will still get you the correct answer. By all means, as long as you're showing me the work, I embrace different methods. I'm not one of those teachers. I'm one of those teachers. I will show you my method. But in the end, if someone shows me their method, I always encourage their methods. And if we were in the class, I would always encourage students to share their methods with others, because, hey, maybe students aren't getting my method, but maybe they might get someone else's method and someone else's explanation of their method. So I always encourage that. So understand that I'm not one of those teachers like very picky that it's got to be done. There's certain things that I'm very picky about, like making sure that you have units for your answers, that you're rounding accordingly. But it doesn't quite matter. Let me just attend. There's just a question, a comment here. So someone had asked, do I always? So you'll notice here I've got grams per mole, because they cross out, because they so-called cancel out, and understand that the term canceling out is actually a misnomer when it comes to math, because canceling out implies zero. When you cross out formulas, they actually, or the units, they actually equal 1. Okay, but anyway, that's for another lesson. You don't need to show them, and the reason for that is because the end result is not, these units aren't going to help with the units that you're going to end with. So in this case, excellent question, by the way. Thank you for sharing it. It is not going to be necessary to show these. I show the units because I want people to get, just to get into the habit of using the units, because nothing's worse than seeing people not knowing the units and just kind of making up units for what they think. I'll be asking, what is the mass of something, and then their final answer will say moles, and it's not because that they slipped up, but clearly from the question they don't quite understand what the units are. So, but in this case, I'm fine with you not sharing the units, just because they actually will cross out. Grams per mole up here divided by grams per mole here will give me no set units. The only unit that comes in at the end is that percent, and that's based on us multiplying by 100. Okay. Any other questions before we move to the next lesson? None. Okay, so let's move on. Empirical formula and empirical formula of compounds. So here's where things can get a little bit tricky. Okay, so please bear with this. Okay, because this, like I said, things can get rather tricky. Okay. So, John Dalton stated that atoms combine with one another in simple whole number ratios to form compounds. So, H2O shows that one molecule of water contains 2 hydrogen atoms and 1 oxygen atom. Now, what this means is, if you ever look at a formula, you'll notice that no formula has any decimals. So all formulas are whole numbers. Think of glucose, C6H12O6. We don't have decimal values or fractions for formulas. They're full whole numbers. Okay, so that's what Dalton stated, that compounds will contain whole number ratios. And those ratios are based on those little numbers, those little subscripts. But as I mentioned last class, those little numbers, right? There's this H2 and an O. This O implies 1 oxygen. It means that I have 2 moles of hydrogen and 1 mole of oxygen. Okay, so understand, and it'll help us out with this this lesson if we understand that those little numbers imply moles. Okay, next slide here. Actually, sorry, there's something I forgot. So we have 2 definitions here. Okay, let me bold them. Empirical formula and molecular formula. Molecular formula is the actual formula of a specific molecule. Okay, C6H12, H2O, NaCl, MgF2, right? So the actual formulas of actual compounds are molecular formulas. I'm introducing now a new term, and this is what is referred to as the empirical formula. And what the empirical formula is you're taking the actual molecule's formula and those little subscripts that make up that formula, you are going to simplify them all to lowest terms. Understand that some molecular formulas cannot be reduced any further than they already are. Prime example here, H2O. H2O cannot be further simplified because there's 1 oxygen, can't go any smaller than 1. And remember this expression that I just mentioned, that lowest being a 1, because it's going to come in to play later on in this section. Understand this section can get a little bit tricky. I can't stress enough for you to practice the questions. Okay, practice the questions, because practicing these questions will hopefully make things a little bit simpler, because these can be a little bit tricky. So what I think I'm going to do is I think I'm going to wrap up tonight's lesson with just this. So we won't do 7.3 just because I want to make sure that we grasp this one. 7.3 is an extension of what we're doing now, but it's very simple in comparison to 7.2. So 7.2 requires a little bit of thought process, because there's a whole process of things that you're going to need to do to get to the final answers of these type of sample problems. But anyhow, the empirical is the simplified version of an actual molecular formula. And so here in this next slide, I actually have this comparison of the of molecules and their molecular formula with their empirical. So take, for example, an example we looked at earlier today in 7.1 when I gave the example of hydrogen peroxide. Hydrogen peroxide is H2O2. So that's the actual molecular formula. Now, if we take that H2O2 and we think, what number divides evenly in all of those coefficients, or sorry, those subscripts, and that is a 2. So they all simplify to just an HO. So 1 hydrogen for every 1 oxygen. So the ratio is a 1-to-1 ratio. Water, on the other hand, right? Its molecular formula is H2O, but its empirical formula is also the same thing. Okay, so understand that like in this case, some of these can actually have the same molecular as they do empirical formula. Here's another example. Acetylene, C2H2 can be simplified to CH. That's not the molecular formula. That's just the empirical formula. The empirical formula is going to be something that we are going to be figuring out based on what we did in 7.1. Okay, so 7.1, 7.2, they go together. Yes, 7.3 does go together, but it just adds one more additional step. We're going to focus on on this one, just because there are a number of steps that you have to do to go about solving a problem. Here's another example, benzene. So benzene formula is C6H6. And so if we simplify this, we divide both atoms by 6 to simplify to CH. So the empirical formula of benzene has the same empirical formula as that of acetylene. So here's the funny thing about these two. Okay, these two, and let me change the colors of these. Okay, the funny thing about these is if we go back to 7.1 and I ask you find the percent composition of acetylene, right? You would go about doing the same steps as we did in 7.1. And then if I ask you find the percent composition of carbon and hydrogen in benzene, you will notice that they will both have the exact same percent composition. So they will have the same percent composition because they have the same empirical formula. So when two molecules share the same percent compositions, they share the same percent compositions because their empiricals are exactly the same. Notice when we were talking about water and hydrogen peroxide, they would not have, even though they both contain hydrogens and oxygens, they will not have the same percent compositions because they don't share the same empirical formulas. So take, for example, you're a forensic scientist, you identify some unknown substance at the end, at a crime scene. And using your calculations, you identify that the unknown substance has carbon and hydrogen, and it will create it's a compound whose empirical formula is CH. So you've now associated anything else that doesn't have an empirical formula of CH is not that unknown substance. And that unknown substance will share the same empirical formula. But it will not help us determine what exactly would that unknown substance be. To find that out would be what we would be doing in 7.3. Okay, but for now, what I want you to understand is that percent compositions of compounds that share the same common empirical formula, okay, will have the same percent compositions. Okay, compounds that don't share the same empirical formula but share the same type of atoms in their formulas will not share the same percent compositions. Okay, here's another example. Aniline. Its molecular is no different to its empirical. And glucose, and we're going to see a little more about other derivatives of glucose or other molecular formulas that share an empirical formula with glucose next class when we do 7.3. You'll notice that this C6H12O6 can be simplified to CH2O. So there's a number of compounds that will share the same empirical formula as glucose. Okay, so glucose will share the same percent composition as others that will have the same empirical formula of 1 carbon for every 2 hydrogens for every 1 oxygen. Okay, so how might some of the questions up until now be for this chapter? I might give you a molecular formula and say, hey, find its empirical formula. In which case, you would take the formula and then try to find a common divider in all the atoms of that molecule. And understand that in some cases, as we have here, they will not have a number that divides evenly in their molecular formula. Okay, so let's move on. So compounds may have the same empirical formula as I was mentioning, empirical formula, but with their molecular formulas may exhibit completely different properties. Okay, so acetylene and benzene both have different chemical properties. Both will have different molar masses, but if you were to find the percent composition of benzene and find the percent composition of acetylene, you will notice that they are both exactly the same. Okay, so it'd be very difficult to decipher just on the empirical formula alone which unknown substance it is, but it at least helps us narrow out narrow it down to a select few molecular formulas. Okay, here's a note to be aware of when you're doing these calculations. Two things, because what we're going to see in these sample problems is we're going to be trying to figure out the empirical formulas. Okay, so things to keep in mind: how to use the mole equation. Okay, how to use the mole equation, and the lastly, and this most important, or just as important as the first one, most, but not all, most empirical formulas will simplify to one. That one of them, at least, if not both or all three, will simplify to a one subscript. Okay, like think of the example like this CH empirical formula that we got for benzene. Right, there's one C, there's one H. All right, in H2O there was one O. Okay, so understand that sometimes, many times, most of the times, one of the atoms will actually simplify to one. So the goal is to always try to reach that step. Anyhow, let's look at the sample problems, and this is where so we're going to take these up, but I do want to discuss it, how to go about answering these. So in this sample problem, calculate the empirical formula of a compound that is 85.6% carbon and 14.4% hydrogen. So these percentages are what we did in 7.1, finding percent composition. Now we're going to kind of go backwards, but not necessarily backwards. So what we're trying to do here, okay, is this. We are trying to find the empirical formula. And this empirical formula is some kind of, put an N. Actually, let me put an X here, an H, and a Y. And let me actually take the time to put subscripts here. Okay, format. Okay, so let's format this. Okay, so this is what we're trying to find. We're trying to find some C something, H something for this problem. Okay, as I mentioned last class, and for those of you who weren't here last class, I have posted all the conferences that I've had with whatever students who've been coming on the past several Mondays and Wednesdays since we finished our March break. All those videos of those lessons can be found on my YouTube channel. So feel free to go and catch up on them if you like, or just read the notes. You don't have to watch the videos, or even find somebody else's videos if you don't want to listen to me again or at all. So there's many resources for you to kind of venture off. I will share mine because they're the ones I put together. But anyhow, what I mentioned last class is that these little subscripts in formulas, and I think I also mentioned it earlier today, they represent moles. So instead of this CX and HY, let me put N. Okay, and I'm putting both the same. Okay, but think of it as an N1 and an N2, a different number of moles. So think about how we calculate moles, right? We think about the pyramid that we learned last class, or that triangle, the magic triangles. To calculate the number of moles, it's equal to mass divided by molar mass. Okay, now, we don't have masses here, right? But we can find the molar mass. So, in other words, I can find the moles of carbon using this formula, and I can use, and let me copy that out. I can find the moles of hydrogen using that same formula. So the molar mass of carbon is 12.01 grams per mole. Actually, we're not going to need the formulas, but you'll see that in a moment what we're doing. And for hydrogen, the molar mass is 1.01 grams per mole. So actually, let me get rid of them because there are too many slashes, and that might confuse some people. So we're trying to find the N1 and the N2. Those ones and twos, it's not a special formula. Really, I'm just trying to find the number of moles. Okay, I'm just trying to find N. Okay, I put an N1 because it's implying the moles of just carbon. Okay, so the moles of carbon is equal to M over 12.01. The moles of hydrogen is M divided by the molar mass of hydrogen. Now, what is the mass? If you look at the percentages, we've got 85.6% and 14.4% to give us a total of 100%. So when we have these kinds of percentages, what we want to do is pretend. Let's pretend that our sample using these percentages is based on a 100 gram sample. So if they're based on a 100 gram sample, what would the mass be of carbon? And the mass for carbon would be 85.6 grams. Okay, so so we have the grams and then the grams per mole, and so grams would cancel out to give us moles. Okay, let's do the same thing for hydrogen. Hydrogen, right? The mass of hydrogen in this example, we're going to pretend we have a 14.4 gram sample, right? Because if we take the two percentages together, we add them together, we get a sample of 100%. So let's just pretend that our sample is 100 grams. And in which case we can actually use this. Okay, so let's actually look at what we are doing. So here's the process. So for carbon, we took the percent, we converted it to a mass. We divided it by the molar mass of carbon to get this big number of moles. And then we did the same thing for hydrogen. We took the 14.4 grams, we divided it by 1.01 grams per mole to get this many moles of hydrogen. So what I did here, this C7.12739 is right. That is the subscript for carbon. Hydrogen, this is the subscript for hydrogen. So doesn't it look like it's a really big formula? C and C7 and H14. Remember, based on what Dalton said that molecular formulas are based on whole number subscripts. That's not a whole number. We want to make it a whole number. Okay, so we don't just round it. Okay, we need to do one more further step. So the further step that we do, and this goes back to the note that I left. Most empirical formulas simplify to 1. So from this step here in the middle, how do I get a 1? I divide both atoms by the lowest number that I just calculated. So carbon had the smallest number of moles calculated between the two. So if I divide both of them by the smallest, I will reduce this carbon's empirical formula to 1. And hydrogen's empirical formula will simplify to a 2.000037. So the more numbers you have, the better off you're going to be for this empirical formula. So I can't stress how important it is to carry the numbers over a little bit. Okay, so the empirical formula in this example works out to CH2. Okay, so this unknown substance that is made up of 85.6% carbon and 14.4% hydrogen will have an empirical formula of CH2. Now, earlier in this lesson, we looked at a couple of examples that contain carbon and hydrogen. Could this be benzene? Could this be acetylene? And the answer would be no. Should be a clear no, because both of those examples that I just stated, benzene and acetylene, have an empirical formula of CH. This unknown substance empirical formula is CH2. Okay, so to recap, to calculate these empirical formulas, these are the steps that you're going to take. Here, these are nice and easy because there's only two atoms. If there was a third atom, you would have a third atom here along the way that you would be searching, and then looking at the three that you calculated up here. Okay, the three that you calculated up here, those you would still divide by whichever one of those three happens to be the lowest coefficient. Okay, let's move to the last sample problem, and this one's a little bit tricky. It follows the exact same way as we do question one, but there's an additional step in number two that you need to be careful of. Okay, so let's look at question number two. So the percent composition of a fuel, some unknown fuel, is 81.7% carbon and 18.3% hydrogen. Find the empirical formula of this fuel. So, same thing as we did in the first one. Okay, in the sample problem number one, we take these percentages and we make them grams. Okay, so we've got 81.7 grams, we've got 18.3 grams of hydrogen. We divide the carbons by its molar mass. We divide, right? Because remember, what are we trying to do? We are trying to find the N values. We're trying to find those numbers of moles in that empirical. And that's what we're doing with this calculation of little m over big M, right? Mass divided by molar mass. And we get the N value. So we take those N values and they now represent the subscripts, okay? They represent the subscripts of our empirical formula. But understand that Dalton said that we need whole numbers. So we don't just round this. We don't round this to C7H18. We always need to keep in mind that most empirical formulas simplify to 1. So how do I get one of these one of these atoms to simplify to 1? And that is to divide by the lowest of the two sets of moles. Okay, and the lowest number is the one for carbon, and that ones out our carbon. So carbon will have our 1. However, when we divide the lowest number with hydrogen, we get 2.66. 2.66 is a number. Yes, we could round, but to round, the numbers after this decimal need to fall. And this is a slide that I introduced a little bit earlier, but I don't introduce it yet. The number. So remember, the number that we just got here ends in 2.66. 2.66 does not fall within this range, a 0.9 ending to a 0.99 ending. So if it falls within this range, you can round off, the number can be rounded off to the nearest next whole number. If it's between this range, 0.01 and 0.1, it could be rounded down to that nearest whole number. 2.66 is way off, rounding it up, way off from rounding it down to 2. So we need this table here, and you don't really need the table, right? But this coefficient here, this 2.66, lies right here. The times 0.67. Okay, it's close enough. So it means that we have to multiply both of our atoms by 3 to get a proper empirical formula. And that's what that last step here, that's what this writing in purple is, this times 3, because in this case, we've actually come across an empirical formula that doesn't necessarily simplify to 1. In this case here, the empirical formula of this fuel is a C3H8. This doesn't mean that this is the molecular formula of the compound. It means this could be the molecular, but it could also still be the empirical of a much larger formula. Okay, so I am going to wrap up the recording there. I will take questions right now. I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.